Hey guys, welcome back to another video. In this video, we're going to solve a few hard questions from organic chemistry, that is from A2 level chemistry. I've already solved 6 questions, and from this video, I'm going to solve 7 and onwards. So this is the first question for this video. It is from summer 22, paper 4.1, and this is some part E of that paper. And it is saying acyl chloride reacts with sodium carboxylates to form acid anhydrides, shown in figure 5.1. Acyl chloride reacting with sodium carboxylate, forming acid anhydride. Okay, and this is forming NaCl as a byproduct. How? Because this Cl and this Na is reacting, and this O bonds with this carbon atom, right? This O bonds with the carbon atom, and it forms acid anhydride. Fair enough. So the next part is saying the condensation polymers, polyanhydride, polyester, are formed by similar methods. Okay, the repeat unit of polyanhydride is shown. So this is acid anhydride, right? And they tell you polyanhydride, that is a polymer made up of monomers of these type of compounds, is going to look like this. And these are similar to, they are saying, polyesters, where ester bonds are created. So what I'm understanding from this is, even in this case, ester bonds are created, because they're telling you polyesters are produced in a similar method. Hence, I know that in this case, if I hydrolyze this, they're asking you in part 1, use figure 5.1 and 5.2 to suggest the structure of the two monomers used to make this polyanhydride. Hence, if I break this, I'm going to break this from the ester bond, right? So they've already told you that this is one repeat unit. So it has become a bit more simple. Since it is going to act like an ester, the only ester linkage over here is where? Over here. This is your ester linkage, so break it down from here. And they asked you to relate with this figure. Relate with that figure 5.1. Notice, to form the polymer, to form this acid, what had happened was, one was sodium carboxylate, where this oxygen is bonded to Na. And another was acyl chloride, where this C had Cl bonded to it. Now notice one thing. Over here, this is not going to form a polymer. Why, you ask? Because the structure ends with R. This structure ends with R. So no other acid can join over here forming a bond. However, if rather than this R, there was, let's say, ONA, and rather than this R, there was, let's say, Cl, what would have happened? This, another structure similar to this, let's say this C, Cl, O, C double bond to O, O, and this is going to be ONA. So this Na and Cl would again form a bond similar to this, and it would form a polyanhydride, or I mean a polymer, right? So it would have multiple repeat units, because I'm reacting this sodium carboxylate, similar to this sodium carboxylate. I'm just substituting this R group with ONA as well. So both of these sides are going to be ONA, right? The salt group, right? So in case of acyl chloride, what am I doing? Instead of R, I'm adding Cl. What's the benefit of it? I can add multiple monomers of these to form the polymer. My ultimate organic product won't end with one repeat unit, right? It will continue forming a polymer with multiple repeat units. So I need to break this down from over here such that it can create polymers similar to this. Similar to, instead of R, there will be Cl, and instead of R, there will be ONA, such that the repeat units can repeat, right? Okay, so what's going to happen over here is if you break this from here, from the ester linkage, hydrolyze it, notice one thing, this part is similar to something. This part is similar to your ONA. C double bonded to O over here, and there's supposed to be Na over here, and C double bonded to O over here, there's O over here, and there's supposed to be Na over here from in case of the monomer, right? So it's acting as sodium carboxylate. This group is acting as sodium carboxylate. So if in this case it didn't have two carboxylic acid groups over here, because I mean, instead of Na, if you have the H, it's going to act as a dioic acid, but there is Na over here, so it's acting as salt. Anyways, so in the case that you didn't have two ONA bonds, this wouldn't have been a polymer, because you know from studying polymers, that is polymerization reaction, forming ester bonds, amide bonds and all that. In case of having dioic acid and diols, if you go through esterification, it can form repeat units, right? It can form repeat units. Similar to that over here, if you have carboxylate group in both positions, it can repeat. There will be repeat units over here, right? So I am breaking this down into ONA in this side and ONA on this side as well, and this is going to be NaO, C double bonded and CH2, 3, C double bonded to O and O Na, right? And the other part is going to be this, which is again similar to what? Notice it is similar to this. So I'm going to break this down as, I'm not going to draw this atrocity, I'm going to draw it as this. C double bond O, Cl, C double bond O, Cl, right? This is your other monomer. Fair enough. So this is your question 7. And this process is, by the way, hydrolysis. Moving on, question 8, Q8. Now, question 8 is telling you, this is easy. Part B is telling you a series of 9 separate experiments if carried out as shown in table 5.1. Complete the table by placing a tick in the relevant box. If a reaction occurs, place a cross in the box if no reaction takes place. So basically, they've given you a bunch of reagents with acids. Yeah, acids. They're telling you if the reactions will take place. Benzoic acid destroyed. Benzoic acid. COOH. And you have phenylmethanol. C6H5. They've given you the structural formula. C6H5, CH2, CH2OH. Okay, so phenylmethanol. What else? Phenol. Our good old phenol. These are your 3 organic compounds. But all of these are what? Acids. Okay. All of these are acids. Now, in these cases, what's going to happen is they're going to go through acid plus metal reaction or acid plus base reaction, or again acid plus base reaction. In case of benzoic acid, it is relatively a strong acid, hence a typical carboxylic acid, which is why it is going to go through all acid plus metal reaction, acid plus alcohol reaction, and acid plus carbonate reaction. This is weak base. Weak base, right? But due to the carboxylic group, it will go through all of these reactions. It's a relatively strong acid compared to these, at least. Now, in case of phenylmethanol, notice phenylmethanol, where is this? This is alcohol group, hydroxy group attached into the long chain. Now, in case of typical alcohols like this, CH3OH or CH3CH2OH, in these cases, notice these only react with reactive metals, right? These only react with reactive metals You should know this from AS level. So these type of molecules or alcohols will only react with reactive metals such as sodium. These will not react with aqueous like NaOH or alkali. It won't react with alkali. The other thing is it's also not going to react with sodium carbonate because this is a weak acid. Okay, sorry. Why am I saying weak acid? Weak base. So since it is a weak base, it's not going to react with sodium carbonate, right? Now, since NaOH is relatively a strong base or strong alkali compared to this, since it is weak, it will definitely not react with the sodium carbonate. Since you already know it doesn't even react with sodium hydroxide. Okay, now in case of phenol, what's going to happen? Phenols, react with Na because you've seen the reaction when studying organic chemistry. It's basically going to create hydrogen gas as your byproduct, right? Yeah, it's going to create hydrogen gas as your byproduct, like a typical acid plus metal reaction, right? And it's going to create this phenoxide ion. Okay, and in case of NaOH, it also reacts with NaOH aqueous solution. You have seen this when creating phenoxide ions, right? Aqueous solution of phenoxide ions. It's great. So in case of phenols, it reacts with reactive sodium metal. It also reacts with your NaOH. However, it will not react with sodium carbonate. Why? Because it is a weak base. It is a weak alkali, which is why it is not going to react with phenols. Now that is your question 8. Moving on, question 9. This is part 7 of summer 23. Question 7 of summer 23, paper 4-2. A is easy. Pardon me. Iodine monobromide. Okay, yeah. Iodine monobromide reacts with benzene in the presence of AlBr3 catalyst. Predict whether the organic product will be bromobenzene or iodobenzene. Explain your answer. Interesting question. Now, when explaining in my crash course, I explain one thing. The Br and Br will break to form, will break via heterolytic fission. One will be an electrophile, one will carry a negative charge. Uneven distribution of charge. Even in case of iodine and bromine breaking, one will carry a negative charge, one will create a positive charge. The one that creates or has a positive charge is going to be your electrophile. Now, seeing the catalyst, you may imagine that since there is AlBr3, obviously it is going to be, bromine or Br plus electrophile substituting your hydrogen atom of the benzene structure. But that is not the case. The thing is, in case of iodine and bromine, which one is more electronegative? Bromine. Hence, when heterolytic cleavage takes place or fission takes place, this bromine will form bromide ion, and this iodine will actually form the iodine positive or iodine plus. Since uneven distribution of charge, and which one is more electronegative? Bromine. Hence, it takes a negative charge, and iodine forms the electrophile, which is why this electrophile will now substitute the hydrogen atom. This is an interesting question that I found. So, hence, the bromine being more electrophilic, it is going to exist as Br minus, while iodine and bromine molecule or bond is going to break, forming iodine positive ion and Br minus ion, where iodine positive is going to be your electrophile, which is going to substitute your hydrogen atom. Fair enough. That is your question 9. Now, question 10. This is from summer 20 of paper 4-2. Summer 20 paper 4-2. Okay. So, we are going to... Okay. This is your phenolphthalein. Just take a look at it. This is your phenolphthalein. So, now you're going to see how this phenolphthalein is going to react to give you that color change, right? Fair enough. So, this is phenolphthalein again. And part D. Name the functional groups in the addition to benzene present in phenolphthalein. You can find this. Part 2, phenolphthalein reacts separately with two reagents shown in the table. Complete the table by drawing the structure of the organic products formed. part of the structure has been given for you, stating the type of reaction. Now, phenolphthalein, notice this is phenolphthalein, and they're telling you that what's going to happen if you add excess hot NaOH, right? Excess hot NaOH. You should know about alkaline hydrolysis, right? So this is your ester linkage, and this is going to bring you to alkaline hydrolysis, and this is going to be your carboxylic acid COH. However, alkaline, hence it is going to be Na plus, right? Because hydrogen is going to be substituted by your Na, alkaline NaOH, right? So the sodium metal will substitute the hydrogen atom, and over here you have OH. Now OH will stay as it is. Why? Because in case of this OH will stay as it is, because in case of ethanols, you know that they don't react with NaOH aqueous, they only react with reactive sodium metals, right? So this OH, since it is not a part of the phenol structure, it is not going to have its hydrogen atom substituted by Na. However, in case of phenols, notice this H and this H will be substituted by Na. Why? Because phenols react with NaOH to form phenoxide ions or salt, phenoxide salt. So that is what's going to happen. Notice over here that this bond will be breaking and H plus replaced by Na. This H stays as it is. Why? It doesn't react with NaOH. It only reacts with reactive metals. Now, over here, H replaced by sodium metal, H replaced by sodium metal. So hydrolysis takes place over here. The ester bond is broken, and COOH, the H replaced by Na, and this OH stays as it is since it is a part of your ethanol structure. I mean, not ethanol, but since it is linked to other carbon atoms and not to a benzene structure, it is not going to be reactive enough to get displaced by Na, right? So it is only going to react in the presence of reactive metals. Now, the other case, your phenols, they are going to go through substitution with Na plus, right? The H is removed and Na plus is going to join the structure. And this is going to be what type of reaction? Hydrolysis, since the bond is broken. And it is also going to be electrophilic substitution. Why? Because Na plus is substituting H plus. Electrophilic substitution reaction takes place. Okay, now the next one is excess of bromine added, aqueous bromine added. Now over here, notice phenol, and they're going to substitute. In case of phenol, they're going to substitute in 2 and 6 position, 2 and 6 position, 2 and 6 position. So it would also be 4th position, but it is already occupied. And this is going to be bromination. Now, this structure is going to stay as it is, that is your ester structure, since bromine is not going to affect it. Now, you may ask, why is there no substitution over here? There is no directing group over here, for one thing. And the other thing is, in general, you've only studied directing groups such as NO2, phenylamine, NH2, and OH added to the benzene structure, and only in those cases have you seen bromination take place, right? And in case of alkyl groups attached. So other than those, you're not going to consider for a bromination, right? There is no reacting group over here. There is these two bonds added to this carbon and this carbon, which is why identifying where the bromination is going to take place is difficult. So don't consider this benzene structure. You're only going to consider these benzene structures where there is a directing group. There's a direct directing group where it is indicating this, and this, right? These 4 positions, you're going to have your bromine electrophile, substitute your hydrogen. This is different. That is your question 10 and question 11. Question 11 is from 9701, Summer 23, paper 4-2. Okay, so this is saying some question part 2 is saying the reaction shown in figure 5.2 produces okay. No. So part D, acyl bromide RCOBr3, RCOBr can be synthesized by reaction of carboxylic acid and SOBr2. And this is a similar reaction to synthesis of acyl chlorides using SOCl2. R, rest of the molecule attached to carbon, attached to double bonded to oxygen, and Br. This can be synthesized by reaction of carboxylic acid and SOBr2. So basically, to the carboxylic acid, you're adding this Br structure. You're replacing the OH and adding this Br. Okay, fair enough. And this is a similar reaction to acyl chlorides. Synthesis of acyl chloride. So in case of acyl chlorides, what happened? In case of acyl chloride, you had C double bond OH and R group attached. And in case of PCl5, let's say, right, PCl5. Yeah. So in case of PCl5, one of the OH will go. And Cl would replace this OH. Cl will replace this OH. As the byproduct, you would get POCl3, and you would also get H2O. Sorry, not H2O. You would get HCl. Right. So yeah, in case of POCl3, if you added POCl5, you would get POCl3, HCl, and ethanol chloride, or whatever R group is attached over here. Doesn't matter. So these would be your byproducts, right? This and this. Now, in case of producing RCOBr3, they are saying it's similar to reacting carboxylic acid and SOBr3. So I considered PCl5. Now they're asking you to consider SOCl3 or SOBr3. Right, SOBr3. That's going to be a similar reaction. So you're going to have your ethanoic acid between ethanoic acid and SOBr2. And so ethanoic acid reacting with SOBr2, it's going to produce your ethanol bromide and sulfur dioxide and HBr. So it is exactly the same as ethanol chloride production. You would have sulfur dioxide and HCl being produced instead of HBr. That's the only difference. And next part 2, suggests the relative ease of hydrolysis of acyl chloride, acyl chloride, and alkyl chloride, RCl, which is going to be easier to hydrolyze. Now, in case of ease of hydrolysis, you have ethanol bromide, ethanol chloride, and RCl. From the get-go, you will understand one thing, that in case of ethanols, there is a difference in charge between the carbon and the halogen. This will have a more negative charge, this will have a more positive. So both of these, breaking it down, will be easier first compared to RCl. Why? Because R is your alkyl group. This is CH3, CH2. This is going to have an electron donating effect, which is why the CCl bond in case of such alkyls is going to be very strong, right? It's going to be very strong because there is a electron donating group, right? Due to that electron donating group, the bond formed between the carbon and chlorine is strong, which is why it's going to be harder to break. So hardest to hydrolyze is RCl. Now the confusion is between bromine and the halogen chlorine. Now the issue over here is, you would probably guess that chlorine, since more electronegative, it's going to have a greater negative charge compared to this carbon. Hence, it should be easier to break, right? However, that's not the case apparently. What's happening over here is, in case of bromine, notice, in case of bromine, it has a larger radius. In the periodic table, you'll notice halide group, bromine is placed under Sorry. Now, bromine will have a larger radius compared to chlorine. Its charge distribution is greater, less charge density. Great. The other thing is, due to its larger atomic radius, it has a less orbital overlap with carbon. With the carbon atom, its electron, it's going to have a less orbital overlap, right? Due to its greater radius. Now, due to lack of this overlap, the strength of the bond is less, right? The strength of the bond is less. Fair enough. Now, notice these carbon atoms are all sp2 hybridized. These are what? sp2 hybridized. So, the issue, I mean, it is similar to that of, what do you call it? Benzene structures, where you add a bromine or any sort of halide to the structure. So in that case, you see a partial overlap of orbital. Even in this case, you do see somewhat of a partial overlap, but that is much weaker. That overlap is much weaker. And it is the weakest in case of bromine. Now, due to that weaker partial overlap, it will be easier for this bond to be broken off due to that larger radius of bromine atom. Hence, this bond is easily broken off due to less orbital overlap of carbon p orbitals and your bromine orbital. Fair enough. So that is why your C double bonded to O and Br bond is easily broken off. Fair enough. Now, that is your question 11, right? So this was the tricky part over here. In case of question 12, this is from Summer 21 and paper 4.2. Notice this question. A 3-step synthesis of X, C10, H10O from benzene is suggested as shown. So this benzene goes through something, most likely electrophilic substitution reaction, and this long chain is added to the structure by displacing or replacing the H. Step 2, what's happening in step 2? This OH is replaced. And next one. Next, AlCl3 is added. And this is going to join over here, forming this structure, cyclohexane structure. Right. So, question 1, they're asking you, step 1 is the alkylation of benzene by electrophilic substitution. Step 1 is the alkylation of benzene by electrophilic substitution. Use Acyl to represent Cl bonded to this R group. Write an equation for the formation of electrophile from Acyl to AlCl3. Very simple. It will lose this Cl and it will lose it to AlCl3, forming R plus electrophile. So this all will have a positive charge, and AlCl4 is created as an intermediate. Now deduce the structure of W and X. Okay, let's do that. So this Cl, forget about it. This is the electrophile, and this is going to be added to what? This is going to be added to this position. So it's going to be basically in the middle. You have 1, 2, 3. 1, 2, 3. You have 3 CH2, and this electrophile substituted this hydrogen atom and formed a CC bond, right? Carbon to carbon bond. Fair enough. So this substitution took place, and this carboxylic acid group got added. Okay. Now in step 2, what's happening? In step 2, this carboxylic acid, this OH group has been replaced. This OH group has been replaced by Cl. Great. Now, the tricky part is this one, where again AlCl3 is used. Now, this is your clue. Why is AlCl3 used? AlCl3 acts as an intermediate, or acts as a catalyst, where it gives the Cl atom forming the intermediate where electrophilic substitution takes place. Hence, what's going to happen is this chlorine will be lost to this why do I keep saying intermediate? To this catalyst. So this catalyst gains this chlorine atom, forming AlCl4 minus. And there is a partial positive charge over here on this carbon atom, on this carbon atom, on this carbon atom. Okay. So this carbon atom, which will now have this positive charge due to this chlorine leaving the structure, this will act as the electrophile and is going to join this, right? It is going to join this point. So there is already a carbon atom over here. So this carbon atom, its positive charge is going to form a bond, with this carbon atom. So notice one thing carefully, as this Cl atom takes an exit, there is a positive charge on this carbon atom. Okay, so this carbon atom will now have a positive charge, and this acts as the electrophile, which will now replace the hydrogen over here that initially was here and goes through electrophilic substitution reaction, right? So a bond between this carbon and this carbon forms, forming this cyclic structure. Okay, so electrophilic substitution reaction takes place. Okay, fair enough. Now they're asking you draw the structure. We drew the structure, deduce. Okay, part 3 is asking suggest the reagents and condition for step 2. Step 2, what they've done is from carboxylic acid they have turned ethanol group. This is ethanol group basically. How do you turn carboxylic acids to ethanol group? You have it memorized by now. Either use PCl5, PCl3 or SOCl2. So either you use, doesn't matter. And I've chosen to use PCl5. So that is going to be question 12. Okay. I've been a bit fast in this video, but for tomorrow's exam, that's why. So yeah, those are going to be all the questions I do for organic chemistry, and see you in the next video.